Today, we are changing the initial conditions for the Stern-Gerlach experiment. Let's get started. We have been studying quantum mechanics, specifically the quantum mechanics of angular momentum. We've learned so far that, for example, any observation of angular momentum necessarily must be proportional to an integer times h over 4 pi. Additionally, we've learned that spin angular momentum is an inherent property of individual quantum systems, or basically particles like silver atoms, protons, or electrons. Because the spin angular momentum of these particles depends on their species, it never speeds up and never slows down. These two facts conspire to give us a really interesting phenomena that we can only measure the direction of a particle's spin angular momentum at a few distinct or quantized values. For particles with the smallest non-zero value of angular momentum, spin angular momentum allowed, h over 4 pi, there are only two angles, and those two angles are 0 and 180 degrees. Last time, we explored the very first experimental evidence of this fact in the Stern-Gerlach experiment. This time, we're going to augment the Stern-Gerlach experiment slightly by adjusting the initial conditions for that beam of silver atoms. The Stern-Gerlach experiment used a beam of silver atoms, which was generated by a thermal process. That is to say, we took a lump of silver, put it in an oven, and exposed that oven to some heat. That heat caused silver atoms, individual atoms, to sublimate off of that lump and start to float around in the oven. Of course, we poked a pinhole in the side of the oven, which created a spray of silver atoms out one side, and we focused that spray into a beam by placing another screen with another pinhole inside of it. Now, we say that they were created thermally to emphasize 2 points. First, that heat was used to free those silver atoms into a beam, and second, to emphasize that there was some component of randomness to this beam. Inside the oven, the heat, which caused the silver atoms to sublimate, caused them to sublimate in kind of random directions with random velocities and random kinetic energies. The statistical distribution, if you like, of the speeds and energies of the individual silver atoms are, of course, directly related to the heat, the temperature of the heat source that we expose the silver to. Similarly, the directions of the spins of those silver atoms were essentially completely random. Now, unlike the magnitude of the velocities of the silver atoms, the magnitude of the spin angular momentum of each silver atom is always the same. It's a precise property of silver. It is just h over 4 pi. The direction of those silver atoms is the thing that is randomly distributed. Remember also that when we say that the direction of the silver atoms is spins are randomly distributed, what we mean is this is before they are observed. After they are observed, of course, there are only two possible directions that those silver atoms can have. They can either be at 0 or 180 degrees with respect to that Stern-Gerlach magnet. And to understand this before and after observation distinction, it helps to recall that we can actually, in principle, place that Stern-Gerlach detector at any angle that we want to. So 0 and 180 degrees is always relative to some choice that we make. To make sure that you understand this fully as an exercise, you might try to explain why, in your own words, the initial conditions of that beam of silver atoms, the spins pointing in all possible directions, totally randomly, leads to a perfect split in the beam of silver atoms to either half going to 0 or half going to 180 degrees. Last time, we spoke about how a uniform magnetic field can introduce a torque onto a magnetic moment like the one enjoyed by a silver atom. While the Stern-Gerlach magnet was not uniform, it was sharply pointed to give those silver atoms a kick. What we can do is take another external magnetic field and apply it. That is to say, we can expose the beam of silver atoms to a constant uniform magnetic field, which will induce a torque on all of their spins and cause them all eventually to align with that magnetic field. Even better, today we'll imagine that we have some knobs that we can turn, which can direct the applied uniform magnetic field to the beam of silver atoms in any direction that we want, so that we can essentially set the initial conditions for that beam of silver atoms so that the direction of their spins is always uniformly pointed in some specified direction. Let's now explore how these new initial conditions can affect the results of the Stern-Gerlach experiment. To be absolutely clear, let's imagine that we have an applied uniform magnetic field B with components Bx, By, Bz in the x, y, and z directions, respectively. The magnitude of this magnetic field, of course, will be constant, large, and uniform. For concreteness, let's specify the direction of the Stern-Gerlach detector, that other magnet, to be in the x direction, and let phi be the angle between our applied uniform magnetic field B and the x direction. That is to say, the angle between the initial conditions, the spin angular momentum of our individual silver atoms, and the detector. In what follows, we're going to redirect the magnetic field into different directions to set the initial conditions for the spin angular momentum of the beam of silver atoms in different directions and see how they influence the results of the Stern-Gerlach experiment. So let's start off with phi equal to 90 degrees. To be concrete, let's specify that the direction of the magnetic field B is purely in the y direction. So the detector is in the x direction, the magnetic field is in the y direction, so the angle between them is going to be precisely 90 degrees. The cosine of this angle, in other words, is going to be equal to 0. So at this angle, well, what do we see? What we observe by passing the beam through the Stern-Gerlach experiment is nothing changes. The beam splits precisely in two once again. Half of the particles go up, half of the particles go down. Okay. Let's change the direction of the magnetic field now to 0 degrees. That is to say, we're going to align B, the magnetic field, perfectly with the detector. We're going to point it, in other words, precisely in the x direction. So now the cosine of the angle is going to be equal to 1 precisely, right? So the angle is 0 degrees. And in this case, what do we experimentally see? What we find this time is that the beam does not split in two. The beam stays together, but is all deflected upwards. Every single silver atom, in other words, is deflected in the up direction. Interesting. Now we're getting somewhere. Okay, let's try something else. Let's reverse the whole situation. Let's try 180 degrees. So you can imagine turning the knobs of our detector so that B is now pointing in the opposite direction. It is pointing against the direction of the detector. It's minus B in the x direction. It's anti-aligned, in other words, with the detector. The cosine of this angle is now minus 1, which makes sense. The angle is 180 degrees. Okay, great. So what do we experimentally see in this case? The beam of silver atoms, once again, is not split, but once again, it is completely deflected. This time, it's deflected entirely downwards. Every single silver atom experiences a kick in the down direction. Ah, interesting. Okay, what's next? But before continuing, it's worth pointing out that there are multiple ways to achieve an angle of 90 degrees. Earlier, we considered B pointed purely in the y direction, but we could have just as well pointed B purely in the z direction. And in fact, we can consider any combination of the magnetic field in the y or z direction. So let's go ahead and do that. For concreteness, let's set B equal to By in the y direction plus Bz in the z direction and see what happens. Once again, the cosine of the angle between the silver atoms and the detector is 0, which is consistent with 90 degrees. Good, so what do we see? Well, once again, we see exactly the same thing that we saw in the first case that we saw last time, which is that the beam is split perfectly in two. Half of the particles go up, half of the particles go down. All right, finally, let's get to a slightly more nuanced case. Instead of splitting into the y and z directions, let's now split into the x and z direction. In other words, let's have some of the component of the magnetic field pointed along the detector and some of the component of the magnetic field pointed in some other orthogonal direction. And let's see what happens. For simplicity, let's just assume that the components in the x and z directions of the magnetic field are the same. In other words, that it's diagonally even between the x and z directions. So since the magnitude of the magnetic field is b, that means that those individual components of the magnetic field are going to be b over the square root of 2, so that the magnitude of the vector is, of course, once again, b. And so what that means is that the cosine of the angle between our magnetic field and the detector is going to be equal to 1 over the square root of 2, which tells us that theta is equal to 45 degrees. Okay, so what do we see now with the beam angled at 45 degrees with respect to the detector? What happens when we pass it through the Stern-Gerlach experiment? Interestingly, almost all of the silver atoms are deflected upwards, 85% of them. 15% of those silver atoms or so are deflected downwards. So we have a non-trivial example of a splitting of the beam, but not even Steven like it's been so far. Evidently, the probability of those silver atoms being deflected upwards at an angle of 45 degrees is much higher than the probability of them being deflected downwards. Interesting. Let's see if we can explain why. We'll revisit the mathematical framework of all of this many times in the next few lectures, but for today, I just wanted to give you a quick overview, a preview, if you like, of the nuts and bolts of how this mathematical procedure works. Like the magnetic field B, the spin angular momentum of any given silver atom is a vector in three-dimensional space. We can write it as, S with components Sx, Sy, and Sz in the x, y, and z directions, respectively. Now, remember, this is the unobserved silver atom. This represents the spin from the silver atom's own point of view. From the point of view of the detector, once detected, the silver atom will only have two options. It'll either be spin up at 0 degrees or spin down at 180 degrees. Sometimes we represent vectors from the detector's point of view in an abstract two-dimensional vector space with vectors like the up vector representing spin up and the down vector representing spin down. Now, from the detector's point of view, before the silver atoms are detected, it doesn't know if it's going to be up or down, so it's going to be some combination of the two. So we can parameterize this generic state vector before observation with two constants, say alpha and beta, so that a generic silver atom can be written in this new kind of ket vector format as alpha times spin up plus beta times spin down. In other words, alpha and beta are constants that parameterize the physical state of the system before observation. What does that mean? Well, we've learned that quantum mechanics is probabilistic. And so actually, as it turns out, the absolute value of alpha squared gives us the probability of observing that particular silver atom in the spin-up state. And the absolute value of beta squared gives us the probability of observing that particle in the down state, or being kicked downward by the Stern-Gerlach device. Since these are the only two options, the two probabilities must necessarily add up to 1. So we have alpha squared plus beta squared is equal to 1. Over the next few episodes, we're going to learn how to relate these individual components of the three-dimensional vectors like S, Sx, Sy, and Sz to these two-dimensional abstract vectors, these components alpha and beta. But for our purposes today, we can just simply guess and check the various values of alpha and beta. So let's go ahead and do that. Clearly, the parameters alpha and beta are going to depend on the angle phi between the spin of the silver atoms and the detector itself. Why? Because this is the only physical parameter in the entire system. This is the only variable that we have to work with. Now, given that alpha squared plus beta squared is equal to 1, we might consider trigonometric functions because, of course, sine squared plus cosine squared is also equal to 1. Now, the naive guess of alpha is equal to cosine phi and beta is equal to sine phi might seem to work, say, for phi equal to 0, because then cosine is equal to 1, and then alpha is equal to 1, which agrees with what we observed in the 0-degree case, but it fails for what we observed in the 90-degree case, because sine of 90 degrees is equal to 1, and cosine of 90 degrees is equal to 0. And at 90 degrees, we observed that the beam split. So in other words, the probabilities of splitting up or down should be equal. And according to this naive guess, they're not. So as it turns out, the correct answer is given by half angles. That is to say, alpha is equal to cosine phi over 2, and beta is equal to sine phi over 2. And this agrees with the 0-degree case. This agrees with the 90-degree case, right? Because cosine of 90 over 2 is cosine of 45, which is equal to sine of 45, which is equal to 1 over the square root of 2. They are the same, which gives us probabilities for finding spin up and spin down both equal to 1 over the square root of 2 quantity squared, which is to say 1/2, which is exactly what we observe. So it's worth checking the one non-trivial case that we had, the 45 degree case. So cosine of 45 degrees divided by 2, if you can plug it into your calculator, you'll find out that it's just a little bit above 0.85. And sine of 45 degrees divided by 2 is just a little bit below 0.15, which agrees precisely with what we observed in the experiment. So indeed, the physical state from the detector's point of view of the silver atoms before they're observed is given by this vector cosine phi over 2 up plus sine phi over 2 down. In summary, we used a uniform applied external magnetic field to the beam of silver atoms to alter the initial conditions for those silver atoms as they approached the Stern-Gerlach detector. Different choices of the angle of the magnetic field led to different choices of the spin angular momentum's direction as the silver atoms approached the beam, which in turn led to different phenomena, different kinds of splittings of that beam as we observed on the detector screen. We also got a little preview of the mathematics involved for how you would explain this kind of phenomena. Next time, we're going to do a slightly different variation of the Stern-Gerlach experiment. We're going to chain multiple Stern-Gerlach devices in series and see how that impacts the final detector screen. Thanks so much for watching. See you next time.